All right, so we have our test coming up on Wednesday. I've gotten a number of emails from online students, and that's good. You know, if things aren't, if the scheduling doesn't work for you, you can, and you're online, you can just contact me and we'll come up with something. So no worries there. If that's an issue, just let me know. We'll figure it out. Okay, so what we got on this exam coming up, just one caution is, in the past I've seen people focus too much on biaxial, you know, because it's the newest thing we're doing and it's kind of complicated. But remember to do this stuff before biaxial. We did quite a lot of things, so remember to go over that and be prepared for it. So we got simple stress and strain. That's kind of like page 200 where we had that block and we applied some different loads to it and saw how it would deform. We have the finding internal forces and stresses when multiple loads are applied. That's like problems 102 and 103, where we're cutting an object open to find the internal forces. Stress strain diagram, modulus elasticity, and all the different characteristics of that curve for problem 111. Modulus rigidity, it's also called the shear modulus, probably a better name for it. That's G, okay, page 180. Poisson's ratio, lateral strain, which means strain from the side, that's problem 122. Axial deformation and with multiple forces is a problem like 152. Statically indeterminate problems, 162 and 3. Temperature-induced strains and stress, so 172 and 3. Axial loading is when you pull on a bar, or push on a bar, I guess, and the loads that are developed then. Remember that even though you're just pulling on a bar like that, you also have shear, so keep that in mind. And then all the biaxial stuff. So on the test on Wednesday, you know, I'll have probably have some elements there where you're finding stresses at angles and principal stresses and things like that. I will not require you to do any more circle on Wednesday. I'll put that on a quiz, which will be available Wednesday through Tuesday in the Red Cedar Hall Testing Center. And also we'll have that quiz in here too on a Friday. So Friday will be half quiz and then half class, okay? So that's kind of the deal. Okay, I got some vocabulary down there, stress and strain, you should know those. You know, you should know the symbols on that page 120 and what those things all mean. And also look over the formula sheet. I'll give you a new copy of the formula sheet that you'll use on the test. You can have a non-programmable calculator, so remember that's a rule there too. So have one that you're comfortable with. I usually bring some, but you don't want to learn how to use a new calculator in the middle of a test. This is not a good strategy. Okay, I've had people do that and have problems come up. It's nothing fancy, but they all have a little bit different syntax and the buttons are in different places and all that. So just be sure you're comfortable with whatever calculator you're going to use, okay? All right, so just some vocabulary there. Remember, there's a lot of these words, they seem to be used in different times and places, but they all mean how much something is changing length or moving in some regard. The good thing about those words is they all begin with the letter D, okay? So deflection, deformation, displacement, delta, they're all delta. They're all a change in length. They're a change in position, you might say. Okay. All right. Do you want to have a look at this review? We could do that if you'd like. Okay. Okay, the first thing there is to find E. That's a stress strain diagram there. Does everybody have a copy of this? Does anybody need one? I'm not sure if I have any more, but we'll look and see. Does anybody got this? Anybody not have it? Okay, we're good. All right, now another thing too is be sure that this is just an example of what some old test questions have looked like. I'm not saying just study this and you're good. It's not that simple, okay? And I didn't really strategize on how I pulled these problems off. I just pulled some old problems off and put them up there that showed a variety of questions I've asked in the past. So this is just to get you an idea what it might look like, okay? All right, so the first thing there is to find E off of this stress strain diagram. So what you do with that is you use the linear portion of the graph. So the straight line portion of the graph is the only place where E applies. So if you start getting up in here, you can't do that. It doesn't have a meaning because E is the slope of the straight portion of the graph. So you just find a convenient point on the straight portion of the graph, which I found right there. So the stress is 2 megapascals, and the strain is just a unitless number, 0.004. So just divide the stress over the strain, you get E. That was about all that happened on that one, okay? And we use E a lot because we design in that straight line portion of the graph. That's where we do our work in. So we use this a lot. Okay. So we got any questions on that? All right, this next one, find the deflection of point C after the load shown or applied. So we have the length of AB, the length of BC. We want to find how far point C moves after the load shown or applied. So what you got to do on this is, I would probably find the reaction first at the wall. So we've got 4,000 pushing to the left with that 2,000 and 2,000 and 5,000 pulling to the right, or I'm sorry, that's 3,000 to the right. And then we have the reaction at A, which would be 1,000 pushing to the right. So that's what the wall is doing at point A. Then what I want to do is find the internal forces. So here's an example of finding those internal forces. Okay, we're going to cut through there and make that into a free body diagram. So there it is. And from that, I can conclude that the load in AB is 1,000 compression. Okay. I'm just going sum of Fx, set it equal to 0. So the load in AB is 1,000. To the left in that free body diagram, which is compression, which means it'll make AB shorter. Okay, then I went with a different free body diagram to find the force in BC. And I just used the simplest diagrams I can, so I'll just use this one. And I'll look at that internal force in BC. It's 3,000 tension. So I found the reaction first, and then I just cut out free body diagrams. And when I make a cut through that shaft there, wherever I cut through then becomes a force that I can solve for using statics. And what I'm doing there is finding the internal forces. Okay? So you make one cut through the object and then include one whole side or the other whole side of the object. That's generally how you do it. The thing that people often do that is not correct is they will say, oh, there it is right there. And that means that that force there is 4,000. They'll cut that, they'll look at that, they'll focus on that 4,000 right there and use it. But you see, when you're doing that, what you're doing essentially is you're cutting through the object twice to pull that little 4,000 out. So if you were to do that, what you would have would be something like that. Okay, and you've got the 4,000 there, sure, but you have to deal then with two internal forces when you do that. That one and that. So you can't just pull a piece out of the middle, because in order to do that, you have to cut the object twice. Okay, so you just can't pull the 4,000 out and use it. You've got to cut through the object and use one side or the other side. So when I say use one side or the other side, that avoids cutting through the object twice, is what it does. So you're only cutting through it once, and then you can solve for where you cut through. That's why I'm saying that. Okay, y'all okay with that? Okay. Find those internal forces, because that's what causes the object to act how it does between A and B, and then between B and C. I found the areas. And then I think I probably just put together a table. There you go. So I've got the load, the length, the area, and the E. And I just run those numbers for each section. I get delta AB is negative 0.001015. Delta BC is positive 0.010685. Add the two together, and I get the net delta, 0.00967. Right there. So that's the approach to that. So that kind of involves two different concepts, I guess you'd say. One is finding those internal forces, and the other is applying the PL over AE to find a delta. That involves both things there. Everybody doing all right with that? You got that down? All right. Okay, this next one, temperature's at 30, and then it goes up to 42. The bar fits in between those two supports with no stress, but also no gap. So it's just in between the two supports. Then the temperature goes up. We want to find the some things about the bar. Maximum normal stress, maximum shear stress in the bar. All right, so this is a temperature thing, so we want to find the cross-sectional area. 0.04 by 0.06, so it's 0.0024. Find the change in temperature, it's 12 degrees C. Multiply that by alpha, and you'll get the strain, 0.006. Now from there, there's different ways to solve it. You know, you can do it many different ways. I just found delta, which is epsilon times L, 0.00348. So that's the delta that would occur if this support were not there, okay? So it would lengthen out like that were it not for the support. So I think of the support as pushing that back. Okay, this is kind of probably the safest, most consistent way that will work every time using this method. Now you can do it other ways. You might be able to kind of do this one a little faster if you did it a different way, but all the same, you know, this is how I'll show it. All right, so we got, so we go ahead then and find delta. It's 0.00348. We know that delta is PL over AE, which is sigma L over E. Sigma is the stress. So sigma is delta E over L when I solve for sigma. So I'm solving for sigma, taking delta times E, dividing it by L. So I'll plug in delta E and L and solve for the stress. It's 16,800 newtons per square meter. Now I'm also asking for the shear stress on that. Now for an axially loaded bar, the shear stress is half of the normal stress. So I'll take plus or minus P over 2A, which is plus or minus sigma over 2. So I got this 16,800 divided by 2, I get plus or minus 8,400. Questions on that?
Actually, could we possibly use Poisson's ratio?
What Poisson's ratio would tell you is how much thicker it's getting.
Oh.
So Poisson's ratio is more about strain, and in particular lateral strain. This we're asking more for stress, so I don't think Poisson's would get you much on it. Other questions? Okay, the next one here, we got a block that's fixed. Those hatch marks mean it's fixed. Okay, so we want to figure out how far point A will move after that load is applied. So probably the quickest way to do that is to apply that formula. So what I want to do first is understand that that's a shear problem, because I'm not stretching the block or compressing it. I'm sliding those planes one across the other. So when I look at, especially when I look at the shape of that, that's that shear going on there, okay? Now, when I see that, what I think about is I can use this formula, a modified version of that formula. That's the one you'll find in the formula sheet. But if you're going to use it for shear, you got to modify it. P becomes V, which is really kind of a trivial thing. It's just a letter you use for the load. But importantly, what isn't trivial is E. E, you can't use E for shear. You got to change E into G. So the shear deformation is VL over AG. Now that's not on your formula sheet, but you can derive that very quickly from PL over AE if you want. It saves you having to go through all this stuff. Okay. So if you use VL over AG, the load is 9,000. The length, let's see, the area is what is attached. That's the hatching. So it's 0.28 times 0.17. It's 0.0476 square meters. The length is the side that's not attached. It's 0.36 meters. Okay, so the area is what's attached. The length is what is not attached. So I can go VL over AG. L is 0.36. A is 0.0476. And then I use G, not E, but G. Typically on these problems, I'll give you just all the material properties. E.g., Poisson's ratio, and alpha. Okay. So you can just plug those values in and come up with delta, 0.05672 meters. Now you could do it on the way that we worked on page 200, okay, and do it that way also. It's a little bit longer, but you know, this is kind of the fundamental definitions. So you can find the shear stress by taking the load over the area. Then solve the G is tau over gamma formula. For gamma, it's tau over G. So 189,076 divided by 1.2 times 10 to the 6. So the shear strain there is 0.1576. And then multiply that by the length, the 0.36, and you'll get to the same answer. These are really doing the same thing. It's just this equation is doing it in a more abbreviated way. Okay. All right. We good with that one? All right. Okay, on this one, we've got these three supports on the tank. There's no stress in the supports. It's a lightweight tank, so there's no stress in the supports. Then we put in 180,000 newtons of water into the tank. Find the force in CD and the deformation of CD after the water is poured in. All right, so what you're going to have here with this is each of these supports will exert an upward force on the tank. They're different dimensions, though. The supports are different dimensions. So what you have are three forces in the y direction. So the important thing on this is you need to recognize this as being statically indeterminate, okay? Because you can't solve for those forces with just statics. You need more than just statics to do it. And that's a key thing on on these types of problems is first recognizing them for what they are. That's statically indeterminate. Okay. So what you have then, you can do some things with statics. You do that first, but then you're going to have to apply strength materials to the rest of it. Okay. So the statics, the obvious thing here is that the three loads, when added together, equal the weight downwards. So PAB plus PCD plus PEF is 180,000 newtons. That's the weight of the water pushing down. Okay, so that's going down. All right, so now I could also, as long as things are symmetrical here, I can conclude that PAB is PEF, that they're equal to each other. So that's going to get me down to, with statics, to one equation with two unknowns right there when I combine the statics. So PAB plus PCD plus PEF is 180,000, but PAB and PEF, because they're equally spaced from that central pillar and they have the same dimensions and material properties, they're going to equal each other too. So what that means is 2 times PAB plus PCD is 180,000. So that's as far as I can go with statics. Okay. Now the rest I have to do is strengths, and I can find the areas of the two pillars, the two posts, I might say like that. So now I'm good to go with, I can set up the strengths. Because what I know is all those posts will deform the same. It's just going to move down horizontally and push down on those posts. So delta is PL over AE. So I can put in the load for AB, its length, divide by its area, and divide by E. Do the same thing for PCD, because I know that deltas are the same. Okay. So what I can end up with then when I work through that is that PAB is equal to PCD over 3. Okay. And that's just based on the strengths. Yeah, of course.
Are those deltas the same?
They're the same because everything's balanced there. So the question is, why are the deltas the same? They're the same because AB, the distance from C to A is the same distance as C to E. And those AB and CD are identical. They have the same dimensions, same length, same area, same material property. So when this thing moves down, it's just going to move down horizontally. It's not going to twist. It's not going to be angled.
So do you mean EF? Just
no, what I'm doing, I know that all three of them deform the same. And I've related AB and EF, so they're acting in an identical way. So I'm kind of getting EF out of the equation. I don't want to have to deal with it. So now I'm relating AB to CD, because they're the ones that are different. You good? Okay. Okay.
I just figured it'd be different because that one's bigger.
It's bigger, but the whole thing is just moving down. It's like putting a big chunk of concrete on two pillars. It'll just move down horizontally. As long as it doesn't tip, you know, they'll be the same. Well, yeah, I guess there are all sorts of things that could happen, but yeah, okay. That's the assumption, basically. It's just going down horizontally. And that is key on these, is you have to identify a delta relationship of some type. You know, maybe they're equal, maybe they're, you know, we did another homework problem where there was like that hinge thing, that pin joint on one end, so we did proportions to figure out the deltas. Somehow you have to figure out what's going on with the deltas. In this case, they're equal. Okay, right there. So if they're equal, the load in AB will be the load in CD over 3. So what I can do then is take this substitution and put it in there, because what I want is the load in CD, okay? So I'll go ahead and put that in there. So instead of PAB, I'll use PCD over 3. So I'll have 2 times that, 2 PCD over 3 plus PCD is 180,000. Find PCD, it's 108,000. So once I've identified that load, I can plug it into PL over AE, and I can find the deformation. So that thing, you know, requires you to recognize that it's statically indeterminate. I mean, that's the first step on this. And you need to kind of be looking for that so you can, you know, identify it when it's the case. So you got any questions on that? Good. All right. Okay, then we get into the biaxial stuff. There's a Morse circle problem. Okay, so we could have a look at this one. All right, so what you want to do with a Morse circle problem is identify points A and B. Okay, so we got A is 12 and negative 28. That's based on the element here. So there's 12, there's negative 28, because that would rotate that square of wood clockwise, so that's why it's negative. And then B is positive 72 and positive 28, okay? Now the funny thing with Morse circle is positive shears down, so that the point B goes in quadrant 4, point A in quadrant 2. So I'm going to draw a big circle on my graph paper, put A and B as the diameter of the circle, A is in quadrant 2 and B is in quadrant 4. Okay, so we good with that? Then I'm going to identify point C, which is the average of A and B, so 12 plus 72 over 2 is 42. I don't even need to bother with the y coordinate there because it's always 0. I've got negative 28 plus 28 over 2. I shouldn't have a 0 down there. I'll have a infinity there, or undefined, or whatever you want to call it. So that's a typo. There should be a 2 down there. I put it there because, you know, it ends up being 0. Okay. So now I've got the center point and 2 points on the diameter. What I want to do next is to build a right triangle between A and the center point, like that. That's a right triangle. I can figure out the sides of the triangle. The y side is 28 on account of that. And then this side is the value of A, which is 12. And then I've got 42 minus 12 is 30. That's where I'm coming up with that 30 down there. I'm taking the difference in the x values. 42 and 12. Okay. Then I can get the radius, because that's a right triangle. So the radius is the hypotenuse of the triangle. It's the square root of sum of the squares. It's 41. And then I can find the alpha angle there by taking an arctan of 28 over 30. It's 43 degrees. So we good with that? Okay, that's the setup on the triangle. Okay. Okay, now the question on this stuff is to find the maximum tensile stress and shear stress on the element shown, and the normal stress and shear stress acting on plane CD. So that's what we want to do. So if I want to find the maximum tensile stress, I take the center value, which is kind of your reference point, and then go out by the radius. So I'm going to go out to that point right there. Okay? And I know the radius I just found is 41. So if I take my starting point, 42, and add 41 to it, I'll get 83 megapascals. That's sigma 1 out there. That's the maximum normal stress. And if I want the maximum shear, I just take the radius and put a plus or minus in front of it. So it's plus or minus 41. So that's the maximum tensile stress and the maximum shear in plane. Okay. All right, now if I want to know what's going on plane CD, what I do is I take the angle on the element, which is 58. So to get to plane CD from the vertical plane, what I'm doing is I'm going counterclockwise 58 degrees. So I'll double that and get 106, okay? Twice 58 is 106. So 58 times 2, or excuse me, it's 116. I just have to do my arithmetic there. It's 116. So it's 58 on the element, but the circle is just a model to run the equations with. It's just a graphical model of the equations. The equations are based on angles of 2 theta. So I take that 58 counterclockwise and I double it and I get 116. So what I'm going to do is I'm going to start at A, which represents the vertical plane, and then I'm going to go counterclockwise twice 58. That's 116 counterclockwise. And that's going to get me over here. That's a point on the circle that'll tell me the state of stress on that plane CD. Okay. So I'm starting at A and I'm going counterclockwise 116, which is twice 58. Okay. Now, to solve this out, so are we good with that? We got any questions on what we're doing here so far? We're good? Okay. Now, solving this thing out is based on right triangles. the hypotenuse of the triangle is the radius of the circle. So what I want to know, see, I know the hypotenuse is the radius, that's 41. I want to know what angle that thing acts at. So what I'm going to do is I'm going to take the 116, which is twice 58, so 2 times 58 is 116. I'm going to go counterclockwise, but 43 will get me to the x-axis. I want to know how much further I'm going. I'm going to end up at 73 degrees. Okay. So 116 minus 43 is 73 degrees. So what that means is I've got a right triangle down here at 73 degrees with a hypotenuse of 41. So to figure out the coordinate of that point, which is going to give me the stress on plane CD, I want the coordinate of that point, I do the trigonometry on that triangle. Cosine 73, 41 is 12. Sine 73 times 41 is 39.2. So to get the values then, I'm going to use the 12 and the 39.2 that are the sides of the triangle. I'm going to take 42, which is the center of the circle, and go to the left 12. So that'll be 30. So that's sigma x1. And then I'm going to go down by 39.2. So that's tau x1, y1. And what that is positive, because down is positive. Okay. So there you go. So that's a run through, a little bit of a run through more circle. Is that, any questions on that? Okay. Now the thing on this is there's no set formula to find this angle at 73. It just depends on the geometry of what you're given. I mean, there was one homework problem that I just turned back to those in class where you started out here and then you went that way, right? And you had to get over here. So what you needed to do was to find this angle right there. So it's not like there's a set way, do it this way. You have to look at the circle and look at the geometry and figure out how to get to the angle that you want. Questions on that? Going all right? Now, if you want to practice some of these, keep in mind you have that spreadsheet up in Moodle where you can just plug in values for sigma x, sigma y, and tau xy. You can plug any angle in there and find the stress you want. That's pretty foolproof. So you can just set up a more, use that to check your more circle stuff. Just come up with your own problem, plug the values into that calculator, you'll get the right answer out, and then just check it with more circle and see if it works. That'd be a way of practicing this a bit. I don't know. You've also got the 2 homework problems, the one in class, and now this one. So that's 4 of them too that we've had you cover or gone over. Now the one thing I will say on Morse too, I mean, at the very least, be sure that you can figure out sigma 1, yeah, and tau max. I mean, start with that. Just be darn sure you can do that. That's I think the most straightforward part. But on a test or whatever, you get a lot of points just doing that alone. So just remember to be able to set up a circle, find that. This stuff with the angles, it gets a little trickier. I know that, but all the same, just stick with the principles and work through the geometry. Okay. All right. So any questions on that? Okay, the last one here was to find the stress on a given plane. So this one you have to identify sigma x, sigma y, tau xy. It looks like they're all positive on this one. So all 3 of those are positive. That's positive 110, that's positive 30, and then sigma y here is also positive. and then you'd like to find, so what I'm asking you to do here is to find the stresses on AB. So 48 degrees from the vertical plane. Remember, the 42 doesn't mean anything. You know, I do want to be sure you know the proper angle to use, so I might very well put a couple angles in there. Just be sure that you know which one to use. And for stress, it's from the vertical plane, counterclockwise positive. And then you just plug into the formula. Okay. So I just went ahead and ran through that and got 129 megapascals tension. And then to find the shear, just ran the shear formula. Did I ask you for the shear on that, or just normal stress? Okay. Now, so that was a fairly straightforward one. Then I went ahead and asked if that stress was applied to that plane, what would the element look like after that if it failed? And there's the sketch right there. So that's a positive stress, which means tension. The stress is normal, which means perpendicular to the plane, so it would just pull that element apart. That's where that sketch comes from. Okay. Now, a couple more things on this one, but are we good with that? We got any questions on that? Why don't we elaborate on this just a little bit? You know, these are just old test questions, and you know, I always have to think about the time element, so that's probably why this one was so short. I was thinking about that when I wrote it up. But let's do a couple more things with this, just so we're clear on how to do them, if we're good with that. Okay. So let's say instead of just a plane, I've got an element there. So we'll make that A, B, and then C. So if you want to find sigma x1 for CD, or BC, I'm sorry, BC. Now that would equal sigma y1 AB, wouldn't it? I mean, those are two names for the same thing, okay? Now if you need to do that, and you're on a test where, you know, we all know the clock's ticking and all that stuff's happening, well, how are you going to do that? You got a formula sheet? What's the formula you would use to do that? I think that's the one, yeah, and of course I don't have my formula sheet with me. Yeah, if you want to find that second normal stress, yeah, 31's the way to go, okay? Because what 31 says is that sigma x plus sigma y is equal to sigma x1 plus sigma y1. So that's the quickest way. If you got one stress on an element, a 90-degree element, that's the quickest way to find the second. So don't, remember that, okay? You don't have to run the whole trig formula a second time. You don't have to do 25 a second time, okay? All right, so you go ahead and solve for sigma y1, which is sigma x plus sigma y minus sigma x1. Okay, that's how you do it. Okay. So define that. Now, how about if you want to find tau x1, y1? Okay, what you know is that sigma x, you've got sigma x is 110. You've already written this down, right? Sigma y is 90, and tau xy is 30. So to do this, you're going to use this equation, right? Tau x1, y1, and I think most of us know to use this equation, minus sigma x minus sigma y over 2 sine 2 theta plus tau xy cosine 2 theta. Okay? That's the equation to use, right? Now, what's the angle you're going to put into that? Everyone just think about that on your own. What angle will you put into that formula to find what you want to know? To find the shear stress. So to find, I should fill this out a little bit. To find tau x1, y1 for AB, which angle do we want? That's on your handout too, 40.
Yeah, 48.
Yeah, but if we want to find the shear stress on AB, gotta admit, I'm tricking you a little bit here. What's the angle to put in? Well, it is, yeah, essentially right, into the form. Yeah, it's just 48, okay? Yeah, you're saying twice 48, which is what goes into the formula, okay? And I think, being an engineer is great, but one thing we tend to do is overthink things a little bit, all right? And if you want to find the stress on AB, and AB makes a 48-degree angle with the vertical, it's 48, okay? That's all there is to it, okay? And I'm pointing this out because I've asked this before, and I have people throw these angles in here, and I'm going, where are you coming up with this, and the reason is we're all engineers and we can overthink it, right? And there's also that bit with the principal stresses where you add 45, which I think is where a lot of this confusion comes from. But that is not a principal stress question. That is a simple question. What is the stress on AB? So to find the shear stress on AB, you do the shear formula 26 and you plug 48 into it, the angle to AB. That's all there is to it, okay? So don't overthink it.
In that principal stress problems, we're just analyzing specific angle, whereas this is the max.
No, this isn't. This is a regular, principal stress is the maximum.
Oh.
This is just find the stress on a plane. And this is right off your sheet there, It's just, okay? Now, if it is principal stress, then you got to find the angle first to find, then add 45 to it to find where the tau max is, because tau max acts on a different plane than the principal normal stresses does. It's 45 degrees off, okay? But in this case, it's very straightforward. Just plug 48 into the formula. That's all there is to it. Okay, and I just want to, I've been doing this for years, and this comes up a number of times, so I just want to call it out, okay? That if I'm asking you to find the stress on a plane, just plug the angle in and find the stress on the plane. Now, if I'm asking you to find principal stresses, that's different. You got to find the planes first, and planes, there's two of them. One for the normal, and 45 degrees off of that is the shear. Okay. But this one, I'm not asking that. I'm just saying find the stress on the plane. Okay. All right.
I think what gets me is principal stress. We analyze it more as like a box.
Yeah, I know.
And this is more like a particle along the line.
Yeah, I know. There's a lot of ways to present this information. And, I'm aware that this is a lot of information, and it's got its complexities to it. But, and like I'm just taking this problem here, and that one I'm just saying find the stress on a plane, AB. Right? Now, sometimes the theory is often developed with those elements, and I'm not quite even sure why it's always presented that way. It's just traditionally how it's done. I think of this as more finding the stress on given planes than I do on another separate element. But again, they present it as elements very often. Okay. So are we good with that? All right. Okay. We got a couple minutes here. We got any questions on anything regarding this? I mean, if anything comes up for tomorrow too, I could take them in too for a little bit. But and then we got what? We got homework that's due Friday. Do we have homework due Friday? Okay, that's due Friday. So we'll cover that Thursday probably. Anything coming up? Good. Okay, all right. Remember the deal with the calculator too, non-programmable calculator. I'll bring a box of them, but all the same, know how to run it. That's important. Yeah, TI-36s, TI-30s. There's other brands too. I've got some Casios in my box that are simple ones. The $12 calculators is what we're talking about.
As long as it's like an FE approved one.
Right, yeah, exactly, yeah, right. And they have like a whole website on that, I think. Yeah, so yeah, it's FE approved calculator. Okay.